So, picture this. You leave a hot mug of cocoa on the counter, right? You get distracted, come back an hour later, and it's completely cold. Or maybe you're outside on a hot summer day and you're watching an ice cube melt away into a little puddle on the pavement. These everyday things seem super simple, but they're actually hiding this massive, invisible transfer of power. And it begs the question, where exactly does that energy go when systems change? That is the big, essential puzzle we're tackling today.
Welcome to this explainer. Today, we are diving deep into the fascinating world of thermal energy, temperature, and particle motion. If you've ever found yourself a little tripped up by the difference between heat and temperature, and honestly, almost everyone mixes them up at some point, you are in the exact right place. We're going to break this down and clear up those misconceptions once and for all.
All right, here is our roadmap for today. We'll be covering 1. Where does energy go? 2. The particle model. 3. Temperature versus thermal energy. 4. Tracing transfer. 5. A worked example. And finally, 6. An exit question.
Let's kick things off with Section 1. Where does energy go?
And to figure that out, we have to look at Section 2, the particle model.
To really understand where energy goes, we actually have to zoom way in. We need to talk about the kinetic molecular theory. Now, this is a total foundational concept in physical science. It basically tells us that absolutely all matter, everything around you, the screen you're looking at, the air you're breathing, is made up of incredibly tiny particles. And here is the crazy part. They are never, ever completely still. In fact, absolute zero is the theoretical temperature where they'd stop moving entirely, but scientists have never actually reached it. So in a solid, these particles are packed super closely together, just vibrating in place. When matter becomes a liquid, those particles are still touching, but now they have enough energy to slide and kind of slosh past one another. And in a gas, those particles are widely spaced apart, zooming around freely. They only change direction when they smash into each other or the walls of whatever container they're in. That relentless, constant movement, that is kinetic energy.
Try to really picture this in your mind's eye for a second. Imagine a block of solid ice. Microscopically, it's just this tight, vibrating grid of water molecules. Now imagine steam shooting out of a kettle. Those exact same water molecules are now zooming around like tiny bumper cars, colliding and bouncing off everything in sight. This invisible kinetic energy is literally happening inside absolutely every single object around you right now.
Now for the big misconception buster in Section 3, temperature versus thermal energy.
First up, let's look at temperature. The scientific definition here is that temperature is a measure proportional to the average internal kinetic energy per atom or molecule in a system. I want you to mentally highlight that word average. It's absolutely crucial. When you look at a thermometer, it's not counting up all the energy in the room. It's really just giving you a reading of how fast, on average, the particles are vibrating or zooming around in that specific spot. So a higher temperature simply means a higher average speed of those particles. Okay, now contrast that with total thermal energy, which is sometimes called internal energy. This is the total energy of a system. To calculate this, you can't just look at the average speed. You have to factor in the temperature, the state of the matter, and most importantly, the total number of atoms or molecules involved. In other words, thermal energy cares about mass. It cares about how much actual stuff you have. Here's an analogy that perfectly nails the difference. Imagine a single drop of boiling water floating right next to a massive iceberg. Now, that boiling drop has a much higher temperature, right? Its particles are zooming around incredibly fast, on average. But it has very low mass. There just aren't that many water molecules in one single drop. Now look at the iceberg. Its temperature is really low. Its particles are just slowly, sluggishly vibrating. But because it is absolutely gigantic, it contains trillions upon trillions of molecules. When you add up all that tiny, slow vibration across that massive amount of matter, the iceberg actually contains far more total thermal energy than the boiling drop of water. It's wild to think about, but true. Temperature is just the average, but thermal energy, that's the grand total.
Now that we know the difference, let's look at Section 4, tracing transfer.
So how does this energy actually move? The rules here are beautifully consistent. Step 1, energy always, and I mean always, spontaneously transfers out of the hotter region or object. Step 2, that energy transfers into the colder region. It is strictly a one-way street from hot to cold, never the other way around. And step 3, this transfer continues relentlessly until both objects reach the exact same temperature. We call that state thermal equilibrium. Once those averages match up, the active transfer of heat just stops.
Let's tie it all together in Section 5, worked example.
Picture dropping an ice cube into a glass of warm water. What's actually happening at the microscopic level? Well, the warm water starts with a high average kinetic energy, meaning fast particles. The ice cube starts with a low average kinetic energy, meaning slow, vibrating particles. Since energy always flows from hot to cold, the energy transfers out of the warm water and into the ice cube. And what's the result? The warm water loses energy, so it gets cooler, and its particle motion slows down. The ice cube, meanwhile, gains that exact same energy, which causes it to melt, and its particle motion speeds up. This perfectly tracks the flow of thermal energy until the whole glass reaches that state of thermal equilibrium we just talked about.
And that brings us to Section 6, Exit Question. All right, here is a quick scenario to test what we've covered today. Imagine you have a warm cup of water. You take it and pour it perfectly in half into two separate empty cups. What happens to the temperature of the water in those new cups versus the total thermal energy in those new cups? Think carefully about what temperature measures, that's the average, versus what thermal energy measures, the total based on the number of particles. I'll let you chew on that puzzle for a bit. Thanks so much for joining me on this explainer, and keep looking for that invisible energy happening in the world all around you.